Our speaker for today is Akaki Mamageishvili. He is a researcher at Offchain Labs, a senior research scientist, to be precise. He did his PhD in computer science theory, theoretical computer science at ETH Zurich. And he'll be presenting today his work on economic censorship games in fraud-proof games. So, Akaki, you can start.
Thank you. Can you see my slides?
Yeah.
Okay, let me share it. So, hello everyone. Welcome to the presentation, and thanks for inviting me to this seminar. So today I will talk about joint work with Ben Berger, who is also a researcher at Offchain Labs, Ed Felten, who is chief scientist and co-founder of Offchain Labs, and Benny Sudakov, who is a mathematics professor at ETH Zurich. But ETH doesn't stand for Ethereum, it's a Swiss Federal Institute of Technology. And before I go to our model, let me give you some introduction to motivate what are the fraud proofs and why we should care about economic censorship of them. So I assume you all know Ethereum and that it's decentralized and very secure, but it's not very scalable. And one of the solutions to scale Ethereum, there have been many different solutions, but one of the successful ones have been rollups, and in particular optimistic rollups. And they achieve scalability basically by moving a bottleneck execution of the chain. And let me now describe how rollup functions in general. So users send their transactions to a sequencer. At this point, there is just one sequencer for most of the rollups that I'm aware of, except for maybe based rollups. And then sequencer receives these transactions and orders them in some way. Up to this point, Arbitrum had first come, first serve ordering, but now it's a mixture of first come, first serve and fast lane transactions, but it's very similar to first come, first serve order. But yeah, for the matter of this talk, it doesn't really matter. At some point when there are sufficiently many transactions or too much time passes, sequencer posts batches, or now Ethereum has blobs. So it posts these transactions on the main chain. So if you have any questions, please just pick up. I don't have planned exactly how much time I will speak. And optimistic rollups, they inherit security from the Ethereum using fraud proofs, basically. But the mechanics are the following. The sequencer posts the transaction-relevant data to Ethereum. So there is a designated smart contract that governs rollup. And then there are validators. Before they were designated validators, but now anyone can be a validator, anyone who locks up sufficiently much stake. So one of the validators posts the latest rollup state or a hash of it, because state itself is very large. And that happens with some frequency. I think at this moment it's like 1 hour for Arbitrum 1, but that can be different frequency. Okay, so if other validators don't agree with the state hash, then they can submit their counter claims for the hash, and then there will be dispute resolution, and that's where fraud proofs come in. So fraud proofs are basically interactive protocols that are executed on layer 1, so Ethereum, in the smart contract, and parties that don't agree, they submit their moves alternately. And move here is L1 transaction. Okay, And honest parties, so defender, let's say that defender is the honest party who knows what is the correct state, is guaranteed to win this fraud-proof interactive game if all her moves are included. So that's essential that moves get processed and they are included, and all of them. Yes, there was an old protocol for Arbitrum in which one validator was posting a claim and it could be challenged by any number of other validators. And then they would play this bisection game that I will describe very soon. And one of the players was always losing. What it means is that winner was not guaranteed to be honest party. So all the games should have been played, and that's why it was upgraded to new protocol. But let me give you an intuition what is the bisection game. So players need to have different hashes for the final state, otherwise there is no dispute. And if the hash function is not invertible and you cannot find two different states that have the same hash, that means that you are agreeing on the state. So that means that two players have submitted different hashes, and now they are requested to present a hash of the middle state. And middle is also well defined by those posted transactions by sequencer. So there is a canonical ordering of transactions, so you can find what is middle. And if the middle states are different, then we know that the disagreement arises in the first half. So the game, so this fraud proofs, moves into the first half. And if they are the same, then we know that difference is somewhere in the second part. So the game moves to the second half. And after logarithmically many moves, the disagreement reduces to single step, and single step can be just checked by a smart contract on Ethereum because it's small enough to check, but you cannot check the whole execution. So this protocol was upgraded to Bolt protocol because there was this delay that you need to play all games sequentially, or you can, even if you make some tournament, it will create a logarithmic delay. So in Bolt protocol, mechanics are almost the same, but instead of final hash of the state, players now submit, or validators submit, commitment to a whole computation, which basically what is important here is that anyone can make a bisection. There is only one way to bisect a claim, which was different from the previous original protocol. But what matters here is that, again, we have a bisection. Now, instead of between validators, it's between the claims, but it's still bisection game, and it's alternating the moves. And you need to, as an honest party, you need to include all your moves. And that's what we will study in this paper. What does it imply? So there are actually very few references or related papers to our model, and the closest one is the first one, Censorship Resistance in On-Chain Auctions, recent paper by Fox, Pye, and Resnick, where they look into this economic censorship or this kind of attack, but in a slightly different context of auctions. And for protocols, there are more related papers, how this bisection works, and the earliest one is from previous century, and then there are multiple more recent ones. So our model is very similar to the first paper. So now let me explain what is the challenge period. So challenge period is introduced for fraud proofs because you want to give a guarantee honest participant that all their moves will be included, or if they are not included, then there will be some reaction from the layer 1 or Ethereum. So now it's set to 1 week. It's pretty much arbitrary. It's more like a promise that in 1 week, Ethereum will react to censorship attack. But here the censorship attack that is considered by everyone is strong censorship attack, in which 50%, or in case of Ethereum, it can even be 33%, so 1/3 of L1 stakers can basically block any blocks which they don't like. So the chain, that doesn't continue to grow. So they can block honest defenders' transactions. And that is why this 1 week was set, that if such thing ever happens, then there will be fork from those validators. But we look into a different censorship, and then we are interested how does it play with this 1 week challenge period. And let me now tell you what kind of censorship we are considering. One may not even call it a censorship, actually, because it's assuming just rational validators or rational proposers. So the attacker just bribes the block proposer, or in case of Ethereum, it can be builder, which are delegated parties to build blocks. And the attack is just offering the tip that is larger than tip that defender offers. So defender offers some tip, which is denoted by P. And if the bribe B is larger or equal than P, then block proposer will just take the tip of the attacker. Okay, so now what does it mean for the fraud-proof game? So if attacker bribes successfully, then defender's time is less. So one opportunity to include her transaction is gone. But on the other hand, attacker's budget also goes down, because now only attacker is paying B. And if attacker doesn't bribe, now defender is happy that her job is so she needs to include one less transaction, so she's closer to winning by 1 step. But then defender's budget also decreases, because now she pays the tip P. So it's conditional on inclusion. We want to understand what are the dynamics of these attacks in our context of fraud proofs. And maybe we can see what are the optimal strategies given some parameters, and most importantly, who is winning. So does defender achieve all her transactions to be included or not? Because in that case, we know that she is winning. So let me give you now what are the parameters. We have 2 players, and it's a very simple game, basically combinatorial game. 2 players named Alice for attacker and Daria for defender. We have large T, which is total number of rounds, which corresponds to how many blocks are in the challenge period. Then we have large N, which is number of rounds that defender needs to win, meaning number of transactions defender needs to include in the L1. And we have attacker's budget denoted by A and defender's budget denoted by D. And now we can speculate what are these 2 numbers, A and D. Like T and N are quite clear. T, we can measure just how many blocks are in the challenge period. N is in the bisection, what is the logarithm of the number of steps. But A and D are unclear. But we either take them as abstract values, or we can assume that in case of rollup, the attacker can basically steal all assets that are secured or breached to rollup. And that's actually quite different from the literature in the blockchain attacks, where it is assumed that if you make a successful attack on the blockchain, the value of the at least native token attacker is stealing is decreasing or even going to zero. But here it's different because the value of Ether that is secured by any rollup is not decreasing just because rollup broke. Maybe it will be decreased, but there is no immediate argument why it should get decreased. And we can also argue that defender's budget can be at least lower bounded by the attacker's deposit. Or we can ask attacker or anyone who has right to make moves to have a deposit, and then we can assume that honest party is guaranteed to be paid the attacker's deposit, even in case of, especially in the successful defense, but even in the not successful defense.
So is the
Any
attacker
questions?
challenge? Yeah, is the attacker challenge also a transaction to be posted, or?
No, it's only about state. So that role is of sequencer, and the whatever sequencer posts, that's the canonical ordering of transactions. But state is for attack. Anyone can post what is the state.
So where is he spending money, the attacker, for posting the state? The challenge?
Attacker is spending first, the rollup contract requires deposit, so it's locked in the contract, but then attacker spends here. Attacker has money from outside the system, and it offers block proposers to censor or not include defenders' transactions. So that's where she spends. But if she succeeds, she knows that she can maybe steal all the value from the rollup, because she can claim that all the assets are on her account. So that's why she will spend only up to this amount. So if there is, let's say, 1 billion to steal, you are willing to spend up to 1 billion, or maybe some percentage of that. So we don't specify exactly what are A and D, but we still solve for any values of A and D. And transactions here, maybe I'm not very clear. There are two types of transactions. Transactions that are sent to rollup, that's just information that is needed to update the state of a rollup. And there are transactions that are sent to L1 in the context of fraud-proof gain. So attacker spends money on excluding defender's transactions sent to L1, so Ethereum.
Akaki, you said that Daria's budget can be Alice's deposit if she wins and also if she loses, right?
Yes.
So why can it also be in the case that she loses?
Because this, so this is maybe not very precise statement, but those funds are not on rollup. Those are on L1. So later, after period, that depends also on the implementation, she can be just reimbursed for her try, because those funds will not be stolen, but maybe not. It just, most of the time we expect actually her to win, Daria. But even if something weird happens and later it will be found out that Daria was doing correct thing, maybe she can be reimbursed because those funds are not stolen. Okay, so the question we ask is, how much larger should Alice's budget needs to be relative to Daria's budget. Of course, it will be a function of these parameters, T and N, so that Alice can guarantee victory in the game. Okay? We understand that Daria only needs to win few rounds, N rounds, while there are large T rounds, and that large T is much larger than N. So there is 1 week of rounds, so it's like 50,000, and Daria only needs to win something like 50 or 60. That's why Alice actually needs to have much higher budget, but the question is how much higher? And we study multiple variants of this game, and yeah, so they are characterized by the number of proposers and also proposer types, but I will explain both of these dimensions. Okay, the simplest game is that we have single proposer in each round, and they are rational, of course. And then the round looks like this. Daria offers a bid that is less or equal than her current budget. Then Alice observes B, and then offers a bid that is less or equal than her own remaining budget. And if B prime is larger than B, then Alice wins. Okay, and then whoever wins, her budget is deducted by the amount equal to her bid, and new round begins. So that's basically formalization, what I already said. It's as simple as this. And here we give some advantage to Alice that she's observing what is the bid of Daria, which is conservative assumption for Daria or for the defense, but that's okay. And second, it actually doesn't matter whether or not Alice observes B. Optimal strategies don't depend on ordering of bidding, who bids first. It only depends basically on T and N. It doesn't even depend on, it doesn't even depend on T actually in most cases, but sometimes it does. Okay, so first result is very simple. It's basically characterization, and it says that Alice, so attacker, guarantees a victory if and only if this inequality holds. Okay, so this is this coefficient that you need to multiply D on, and then Alice's budget needs to be larger than this for attacker to win. And actually, proof is almost trivial of both directions, but let's first prove the first direction. So the attacker strategy is that if defender bids more than D over N, so D is defender's budget and N is number of rounds that Daria needs to win, then Alice lets Daria win the round because she knows that Daria is spending too much. Because with this amount, Alice knows that Daria cannot win N rounds. She cannot pay more than D over N times because her budget is only D, and D over N times N is D. And if not, if Daria is smaller than this amount or equal, then Alice matches the bid and wins the round. Also, we are letting Alice win if she is bidding exactly the same as Daria. And that's what she is doing here. And the proof here is, I already said, basically it's written here. But Daria cannot win because she doesn't have enough. And Alice can win T minus N plus 1 rounds. And this is exactly the condition. And the other direction is exactly the same. Daria just beats D over N. And now Alice cannot stop her from winning. So we have characterization result. We know how much larger Alice's budget needs to be. And first, it was quite surprising. We thought it was quite complicated game to solve, but it turned out to be quite trivial. And yeah, it doesn't even depend. Strategies don't even depend on T at this point. So are there any questions about this result?
So this is for a single defender, right? If you have
Yes.
multiple defenders, then for
Oh,
each
multiple defenders.
yeah, for each defender that the attacker outbids, right, the defender does not pay. Only for the last defender that the attacker does not outbid, that defender has to pay. But if you think about that, the attacker, right, pays for all the rest. So
Yeah.
in essence, right?
Mhm.
it
So I
can
think you are referring more to multiple proposers.
no
Like
multiple defenders, multiple defenders.
Yeah, so we
It-
didn't look into multiple defenders, but I think they can just join their forces.
But
think
like actually my point is, if they don't join their forces, right? Let's say Fatima is a defender and I'm a
yes.
defender and you're the attacker. So I bid something, you outbid me, right? Now
Yeah.
Fatima bids something. For you to also outbid her, you would have to pay twice, right? But for us to win, only one of us needs to pay. You see what I'm
Okay, I
saying?
see. Yeah, I see. Yeah, that can be also a helpful point if that
Yeah.
works.
If Sen joins forces, then you have to outbid three of us. We have to win once.
Yeah, I'm trying to imagine how it plays in reality, multiple, because in
Because
case of
you said that
bold,
bold, yeah.
in case of bold, there is one bisection, and whoever is making that, I mean, then I don't see a big difference between you and Fatima and you making bid twice, but you want it to be in the same round. That's interesting. So it's like two competing defending bids, but I would still assume conservatively that attacker observes all bids first and then decides on the like total amount. So if you go again with a conservative assumption, maybe here we are using it if there are multiple, because with single it didn't really matter. So I will just look at how much you are bidding in total and compare to this value. But then also I need to assume that this large D is a sum of your budgets.
Yeah.
Yeah, then it reduces to the single defender problem.
Yeah.
But you are right that I will come to that with multiple proposers, because with multiple proposers, attacker needs to block defender with all proposers. So it needs to pay K times more, but I'll come to that. But yeah, that's a good point. And here, I think it matters the ordering, who observes what and when.
Yeah.
If there are multiple defenders. Nice point, thanks. Okay, so now we can start plugging in numbers. So in case of Arbitrum, let's say at that point we were checking the numbers. The total value that was secured by Arbitrum was $10 billion worth, and there were 60 moves to make in that bisection game. In 1 week, there are around 50,000 blocks or rounds. And in that case, defender needs to have budget at least $12 million. And this is actually quite close to the requirement of a deposit, which is $10 million. So that was like almost accidental coincidence. But next I will show how we can actually lower this requirement on D. Actually, the reality is that some of the rounds are special, and let me describe what is the special round. So in special round, defender offers a bid B again, so it's the same, and then Alice again observes it, but now Alice needs her bid to be larger than K times B, not just B, because of special round. But I will motivate what it where it comes from, and K2. But then the game is the same, or the game in this round is the same. Whoever wins, her budget is deducted by the bid, and then new round begins. So now for characterizing the game, we need T and DA, and also the string of special and regular rounds. So in regular round, we just bid needs to be at least B, and in special round, it needs to be at least K times B. So 0 is regular and 1 is special. And now the motivation for the special rounds. We know that some Ethereum proposers don't use this MEV boost, where they really go through comparing who bids more for what transaction, but they just look at transactions in the mempool, their tips, and sort them by decreasing tip per gas. Of course, per gas, yes. So in case of Bold, the transaction is like 500,000 gas, and we know that gas limit, actually at the time of writing this paper, it was 30 million. Now it's, I think, 36. So the constant would change here. But in case of 30 million, the number is that attacker needs to overpay for 29.5 million gas. So it needs to basically bid in total terms, in real terms, 59 times more, because that's what 29.5 divided by 0.5 is. And that's how, and we assume that nobody is using block space. Of course, if there are some transactions that are using, then this can be even, this will be lower probably, but let's say when such dispute resolution game is happening, stakes are here much higher than anything else. So this will be the highest tip per gas transactions. Okay, so that's the motivation for that constant or special rounds. So constant here is 59, and these are special rounds. In case of 36, now it will be, yeah, something like 71. So question about special rounds. So it's just how some of the Ethereum proposers are using default software for including transactions. And now we have a game that is characterized by these parameters, and now we want to find minimum budget that Alice needs to have as a function of T and D and pi, such that she's guaranteed to win. Okay, and we obtained structural results. First is that A is, so this value, calligraphic A is linear in D. So it's again, we need to find the coefficient, how much larger should it be, the budget. And actually what we found out that was interesting, and I think it needs to be more general property, but we were not really able to prove it. But we were able to prove it for our case of two types of rounds, is that this value is only affected by the number of special rounds and not their location. So not the ordering. So it doesn't matter if you have special rounds in the beginning or in the end or mixed in random. What matters is how many special rounds are during the time horizon T. Okay, so that was some observation we made, and I believe that this is correct even if you have multiple different, more than two types of rounds with different coefficients. But yeah, we didn't prove it. Then we can again look for this value, the coefficient, but now we can drop pi. We can only put number of, so we drop the whole string of length t, but we only put a number of special rounds in that string. And then, okay, so we already have a theorem that this AT and 0 is T minus n plus 1 divided by n. Because if we don't have special rounds, we know what is that coefficient. And now we will try to obtain what are these coefficients in general case. So these are some boundary conditions. So if we don't have special rounds, we know what it is. If defender needs to win only one round, we know how much attacker needs. It basically needs to win all the rounds. And if all the rounds were special, we know what would be the coefficient, because we will take this number and multiply by k. So you take the value here and multiply by k. And so similarly, we can obtain what if the defender needs to win all the rounds. But now we want to solve general form. And we unfortunately didn't obtain analytical solution for it, but we have a recursive formula for it. So this ATNS we can calculate recursively by smaller for the smaller values of Tn and S, Tn and S. And there are these two different types of recursions, and first one is obtained by playing the special round first, and second is obtained by playing the regular round first. And it's actually quite intuitive proof. So let me show you quickly how to obtain, or at least give you intuition how to obtain my first recurrent formula. And so we know that location of special rounds doesn't matter, and I assume that first round is special. So now for Daria to win so let's assume that Daria makes bid B, and now Alice needs to decide between two things: let Daria win round, or let herself win the round. So if she lets Daria win the round, the new state becomes T minus 1 in both cases, actually. But now Daria needs to win one less round. And number of special rounds decreased by 1. And Daria's budget here is decreased by B, because that was her bid. But Alice's budget is not decreased. And then we know what happens in that state. Then for Alice to win, this inequality should hold. The same happens in the other case, except now difference is that Daria needs to win again n rounds, but now Alice's budget is less. And now we know what is the condition for Alice to win the game. So we have two inequalities, and Alice needs to choose between these two inequalities. Now, of course, Alice will take lower of these two values on the right-hand side. And that's where actually Daria comes in, and Daria chooses bid such that those two values are equal, because one of the functions is increasing in B, and another is, so this one is increasing in B, and this one is decreasing in B. So Daria chooses B such that these two lines are intersecting. So we know what is the optimal bid for Daria if the next round is special, and she only needs to know how many rounds are special. And this is the formula. And once you plug in this formula in the calculation, you obtain the recurrent formula. Okay, so recurrent formula is just allowing us to calculate these values, these coefficients, and they can be calculated in basically ns time if we optimize the dynamic programming. So we can calculate, in reality, we can calculate what we should bid if we were defending the fraud proofs and defending against the economic censorship. And now we can also plug in numbers. So instead of yeah, so let's plug in 60 here. If I remember, we assume that k is 60, but it's actually 59. But anyway, if we assume k is 60, we get this coefficient, which is quite large number. But what it results into is that now Daria needs to have budget only $5.6 million instead of $12 million, because special rounds help Daria, or it drains Alice's budget faster. We were not able to solve it analytically, the form of A, but what we were able to do is obtain upper and lower bounds on it, and they are actually asymptotically tied as soon as we assume that n is much smaller than t plus s. And that is quite reasonable assumption, because in reality n is something like 60 and t and s are like 50,000 and 2,000 maybe, or 1,000. Okay, so we obtain this upper and lower bounds, and actually this is obtained by Daria bidding again d over n. But this is not optimal. This is only approximately optimal. And if we look at the reality, we don't know which rounds will be special, but we know the distribution. So we know that, let's say, 2% of the rounds will be special, but that's good enough. If t is large enough, then with high probability, Daria's strategy to beat d over n is again optimal. So any questions here? Yeah, so main takeaway here is that requirement drops almost 2 times for the defender's budget. So it's easier to defend, and we can calculate both precise or optimal beats and also approximately optimal strategy, assuming that Daria needs to win few rounds compared to the number of total rounds. So next we move to extension of this model, where we have multiple proposers, and here we thought this was modeling multiple concurrent proposers case, where all proposers have equal rights to include transactions in the block. So this is a recent proposal for Ethereum blockchain, and I think it is already working on some different layer ones. And there is also a proposal of fossil, so this inclusion lists, where there is a committee of inclusion list proposers, and if main proposer leaves space for them, then they can include their inclusion lists, and those can be used by defender to include her strategy. But probably our models first one better, where they have equal rights, so they don't depend on main block proposer giving them space, but all of them have equal right to include transactions. Okay, so we have again rational proposers, but now instead of one, there are m of them, and Daria includes her transactions if any of the proposers include, which means that Alice needs to bribe all of them to succeed. But now payments, or the auction, very simple auction we had before, is not as simple again, because now the payments, how much they promise to proposers, depends how many proposers will include, or in principle it can depend. And here we are taking simple case for the Alice. So Alice just offers the same payment C to every proposer. That excludes Daria's transaction, and that's, I think, fair enough. In case of Daria, we looked into 2 different payment schemes. In one of them, Daria offers total B, so large B, to a set of proposers who will include, and then if there are multiple of them, then they share it equally. And another one is she pays large amount to the only proposer that will include. Let's say they can write smart contracts somewhere on layer 1. And if more than one includes, then Daria pays each of them the same small b, and small b is, let's say, much smaller than large b. So this is actually payment scheme that we took directly from the paper that I mentioned, Censorship Resistance in On-Chain Auctions. So it was motivated by them. But there is a simpler one here too. So in both cases, we actually obtain strategies or optimal strategies and show the condition when Alice wins and when Daria wins. Okay, so let's say the second one, where we have lower bound on Alice's budget, is almost the same as the lower bound from the trivial characterization result, but it's multiplied by m. So it's m times harder for Alice to win this game, but that's all. So Alice just needs to have m times more to guarantee a victory. So this coefficient is exactly the same, t minus n plus 1 divided by n, and it's multiplied by extra m. While for Daria, it is a bit more complicated. First of all, so this coefficient changes a bit. So instead of minus n here, we have 4 times n. And also, it doesn't guarantee the winning with probability 1, but with high probability. And high is actually very high. It's exponentially close to probability 1. So it's 1 minus 1 over exponential in n number of rounds. And strategies are also very simple. It's basically bidding d over n. And also, we looked at equilibrium condition in the single round. So in the single round, we assume that they find the equilibrium solution, meaning that most of the time it's not pure strategy Nash equilibrium, but the proposers are mixing their strategies, like they are playing at random inclusion or not inclusion, but depending also, of course, on the payments. So the probability of inclusion is solved in the equilibrium. So this is good news for multiple concurrent proposers. For attacker, it becomes much more expensive to censor. Or let's say if there are 20 proposers, it becomes exactly 20 times more expensive. And yeah, asymptotically, here this is basically probability 1, and this number and this number are almost the same if t is large enough. So we have some open questions also. So we studied this problem where we just assume that budget is a constraint. So we only cared about who wins. But what happens if Daria also cares about the budget, especially in case of winning? She doesn't want to pay too much. And if Alice is not bidding very aggressively, then maybe bidding d over n in every round is not a good idea. But that will complicate the target function because now it will include also a budget. In case of bold, the attacker can also play multiple games. In that case, n is larger. But on the other hand, it also needs to deposit more. So defender's budget is also increasing, but it's not immediately clear how to also model that. Also, in our analysis, we only looked at priority fees, but there is also base fees, which sometimes are quite large, or maybe attacker can increase them and change the dynamics of the game. But I don't expect that to help attacker much. But yeah, we are not sure about that. So that's all from me. Thank you for your attention. If you have any questions, happy to answer.
I have a question.
Um,
In the previous slide,
Yes.
yeah, can you give some intuition for one? Bullet one?
For this one?
Bullet one, like for Daria?
This one.
Yeah.
Yeah, so intuition is that there is always a very small probability that attacker is succeeding. And that we couldn't rule out in the equilibrium calculation. So that was bad news for Daria. But this probability really drops very quickly. So effectively, this is basically one.
And this theorem applies to all of the cases that you presented in the slide before this, right? You said that Daria can either bid something that is split equally or bid something big if one includes the transaction.
Oh, yes, yes, yes. So we had this, we fixed Alice's payment and we had 2 payments for Daria. So this solving both. And I actually believe that the theorem is correct, and we have some evidence now that it's correct for much more, like many more different payment rules. But still, we need to have some kind of symmetry and simultaneity. And the only thing that can change is the coefficient here, so with different payment rules. And maybe here too, especially if we start changing Alice's payment rule. It can improve slightly the performance, so she can maybe lower the requirement, but only with some coefficient in front of n, not more. But yeah, mathematics gets too complicated. It's like yeah, a lot of concentration bounds. But if we assume that t is very large compared to n, and also some assumptions on payment rules, yeah, theorem gets much more general. But we somehow thought that these payment rules were the most logical and simplest ones, at least.
So thank you, Akaki.
Thank you.
Maybe someone online has a question.
Hey, I had a question as well. So in this payment rule that you're introducing, if you introduce this sort of a payment rule in a system like Fossil, which currently does not have incentives like built into it, so do you think like the payment rules would just work as is, or would there be like other economic implications in the protocol for Fossil itself, like
Oh,
without the attacks?
yeah, Fossil probably is not a good um, example for these payment rules, because you still want to target main block proposer there.
Right.
But main block proposer, on the other hand, cannot too many times leave out Fossil members, right? So that actually goes to our this future work question: what happens with the base fees? So that would be modeling Fossil more closely, because then one way to leave Fossil members out is to increase base fees, but you cannot do it for too long. And that means that now attacker is deciding between increasing base fees to leave all fossil members out or pay all fossil members. And I think it will choose one that is cheaper, but yeah, cheaper also is not clear because it's a repeated game and there is long horizon.
Right. Okay.
But I mean, in principle, any payment rule shouldn't change fossil too much because I think fossil members will also be rational. I know they are not paid right now for transactions, but they will be paid, right? So addresses will still be there and you can pay tip to fossil member that will include your transaction. So I'm not sure how is the fossil implementation, but you can target the fossil committee member to include your transaction and pay some tip. So what would this change?
Right. So in general, if you add like tips in fossil, you'd be able to like the system would not behave as an any honest. Like the security properties rely on every member, including the first 10 transactions. But if there is tips, then that becomes more complicated, right? Like because you're not targeting censor transactions, you're targeting the transactions which are paying more, and then you'd want to
Yeah,
not target transactions which are being targeted by others because the tip would in your case like you have a higher tip if only one party is included. So I'd try to pick a unique transaction which others would exclude for some reason and give that big tip or something, and that would change the game quite a bit, right?
okay. Yeah, I mean that probably refers to all these multiple concurrent proposers. So we are assuming some kind of simultaneity here, because if you can see that others excluded them, then you can include, and then the payment schemes will also be quite different. But I would assume simultaneity here. So you cannot observe who is including or excluding. You are given some deal. Like there is some agreement. Depending
Right.
on how many will include, after we see the block, payments will be maybe realized in the next block. That's what makes it simultaneous. And censorship and outbidding are, yeah, also unclear. I mean, in this case, if attacker is outbidding defender, you can also assume that attacker is censoring. So fossil members will be motivated to include this transaction. But I believe that if they are also paid enough, they will also exclude. So those are not protocol, how to say, protocol incentives, or protocol cannot control that. Fossil is for me just extra number of proposers who are willing to include your transaction. And then attacker is just losing her budget much faster because there are extra of them. But by design, I don't think fossil itself is preventing censorship. It just makes it much more expensive. So I don't think that fossil is some kind of magic that fixes censorship, but rather it makes it much more expensive.
Right. Okay. Yeah, thank you.